This segment highlights how standardized logging can significantly improve the traceability and reliability of a machine learning pipeline. In this project, logging configuration is managed by Hydra and integrated across DVC, Optuna, MLflow, and Prefect tasks whenever necessary. All logs begin with a shared configuration in configs/logging-util/base YAML. Hydra merges these settings with environment-specific overrides, making it straightforward to direct logs to the console, a file, or both, always following a consistent format. This is the configs logging-utils base YAML file. Let me walk you through it. The first block specifies parameters for pipeline-level logging. We'll see these at work in the example toward the end. We use a pipeline directory directly under logs, and each file within it includes a unique timestamp. The second block sets up our log CFG job logging module. By default, it's disabled, but you can enable it for debugging the job configuration with a single override. Hydra offers an incredibly useful set of tools. We've aimed to work in harmony with Hydra rather than write extra quote-unquote glue code. Each time you run a Python module that includes a hydra.main decorated function, Hydra adds a new timestamp directory for that run. This directory contains every log statement produced by that module, along with the final resolved Hydra job config, any overrides, and all relevant Hydra parameters. Hydra stores overrides in a dedicated YAML file for each run. This separation makes it easy to see exactly which settings were changed, helping you avoid confusion when reviewing logs later. Hydra's job config can stretch well beyond 300 lines, so dropping it into a run log can quickly overload your logs and make troubleshooting tedious. Instead, Hydra logs the config separately in a hidden .hydra directory. Think of it like a debug level statement. By following this best practice, Hydra keeps your main logs readable while still providing easy access to the complete configuration details when you need them. Let's talk about key benefits of this logging. Capturing every step with the unique run IDs is certainly one of them. Another one is centralizing logs for easy search and analysis. And linking logs to version control configurations and MLflow runs must not be forgotten. In a typical workflow, DVC triggers each stage, and the pipeline writes logs detailing data ingestion, transformations, hyperparameter tuning trials, and more. This uniform approach helps maintain awareness of the exact code version, dataset, and parameter set used for any given run. Let's talk about structured logging and best practices. So one of them is use your log levels. They're there for a reason, and use them consistently. Maintain concise logs focusing on key events or errors. Log statements, think of it, it must be either of validation or performance tracking. These are the only two reasons why you would include log statements that are available to standard out. Otherwise, use MLflow or other specialized tools. Let's look at the log file created during a full run of our DVC YAML pipeline. We merge log statements from Optuna, MLflow, and Hydra into a unified pipeline log with a unique timestamp. In this example, DVC runs all stages sequentially, starting with data downloading, then moving through each transformation step. Whenever a stage output differs from the inputs, we create a new data version and automatically compute its metadata. Next, we reach the machine learning stage. Let's go to this. Yes. This stage can look a bit different. By default, Optuna doesn't log much detail during trials, so we added statements to show how many trials will run and how long each one takes. This way, if just 2 trials take almost an hour, we'll know to expect more time for 20 trials. And we can assess this clearly based on the timestamps. These logs also confirm that RMSE, R2, or any other metric that is used in the trial is correctly logged. After the final stage, DVC verifies all data sources and configurations. If everything checks out, the run is successful. At that point, we can push the pipeline's output and logs to remote storage using DVC push, preserving a fully reproducible record of the run. In our pipeline, every single transformation has one function, and tracking the start and the end of that function is extremely important because it lets us monitor the progress during a pipeline run. That's why we created log function call. It lets us wrap each transformation function within this automatic logging function, which enables us to quickly see if a pipeline run is going as it should or if there are problems. With this, we're able to quickly pinpoint where the problem is and how to fix it. It's an invaluable tool for us. Now, let's sum it all up. You should align logging across data, code, and experiment tracking systems. Employ structured, consolidated logs for in-depth diagnostics. And treat logging clarity as a strategic advantage within MLOps. In summary, a robust logging setup constitutes the backbone of an MLOps pipeline. It converts opaque processes into auditable, debuggable workflows. By integrating Hydra's compositional configs with DVC's versioning and MLflow's run tracking, each pipeline step remains transparent and readily reviewable.